Okay, class, welcome back to the second meeting. So hopefully you guys have gotten more comfortable with the kind of the online learning environment. So before we begin, I just want to recap that you should have access to the OWL homework. If you do not, let me know and I'll follow up with Cengage, because the last time I spoke with them, they were working on the issue. Well, I'm not sure if they resolved it yet, but I'll double check this week, later today, probably, to see if that issue has been resolved. So if you still do not have access to the OWL homework, please let me know. It's absolutely crucial that you do have access to it, because the first assignment will be due, chapter 2, the first homework assignment will be due on the 13th of this month. And if for some reason, most of the people still don't have access, we can talk about, maybe pushing back the deadline for the first homework assignment, but that's hopefully it does not come to that. If you want to order a physical copy of the textbook, let me know. Just know that you'll have to purchase it additionally with the OWL code that you already have with inclusive access or equitable access. And also, if you opt out of equitable access, you will definitely be prompted to purchase a code when you visit the OWL site. So just keep that in mind. Okay, so let's get back into chapter 2. So we left off, I believe we talked about chemical change. How do we know we see a chemical change or physical change? So we talked about that. We talked about matter and the states of matter. Now we're going to go into the characteristics of substances or chemical compounds. So we're going to talk about pure versus pure substances and mixtures. Okay, so a pure substance is like something that contains only one kind of matter. For example, like a bottle of water will contain only water, right? Most of the substance is water. You may have minerals in it, like in drinking water, but when we say pure water, there's only water and just water and nothing else. So a pure substance is, let's just jot that down, a sample consisting, consisting of only one kind of matter. And what does this mean? It means it possesses, so let's write this right here, possesses a unique set of physical and chemical properties. And the identity does not change. Does not change with physical change. So even if we boil the substance or we induce a physical change, it will still be the same substance. Okay. So example of this will be anything like a pure liquid, pure liquid, such as water. Okay. So that's an example of a pure substance. So now let's talk about mixtures. Mixtures is sample. Oh, hold on. I forgot to set my timer. So I think that's been like 5 minutes. So we'll just say or an hour and 15 minutes. So an hour and 15 minutes to go. Okay, so a sample of matter that consists of 2 or more pure substances. That have been mixed together. So the reason why we call it pure substance and not just a substance, because a substance is vague and it can contain more than more than two compounds. So for example, like if you have a mixture of water or like seawater, a mixture of water and salt mixed in. So that's why we call it pure substance versus a mixture. Okay, so the thing about mixture is that its properties depend on the substances that are in it. So so each kind of mixture will be dependent on those substances. So properties depend on the substance in it. Okay, so those are pure substances and mixtures. So let's move forward. Okay. Okay, let's see. So for example, if we're talking about pure mixtures, sorry, not pure mixtures, pure substances and mixtures, we can see that if we write our temperature scale here, let's say that we have, and on the bottom we have time. So this is temperature in degrees Celsius. And then, so let's say, this bottom black line here is my water. So my pure substance is water. Now, if I have a solution of, say, water and something else, my curve now will look like this. So this is my solution. So what does this mean? Well, this means that, say my boiling point is right here. So that's my boiling point. So that's 100 degrees. So this will be 100 Celsius. So that's the boiling point of water. So now if I see my solution, the boiling point, so the boiling point will differ, right? So you see how the boiling point of water right there is constant at, you see the line is constant, or we'll know why constant is, the line is flat at 100 degrees. So that means water will always boil at 100 degrees as the pure substance. But when you get a solution, you know that over time that boiling point is going to be changing. See, it's always increasing, and it's not flat, or like a tangent line. It's not flat or constant. So the temperature of the solution depends, for boiling at least, it will depend on the compounds that are in the solution. So solutions, they do not have constant boiling points. It always depends on the composition of the solution. Okay, so some comments we want to make is that pure water has a constant boiling point. And that's one of its physical properties, right? It has a unique set of physical properties, so that's one of them. The boiling point of a mixture, however, the solution in this case, where water is part of it, changes as the composition changes. The composition changes of the mixture. And this line I drew here, so you see the solution, it kind of goes up on the up, and then it kind of bends. That means the composition of the solution is changing. So if you start at one point, it'll have this certain composition and it'll have a certain boiling point. But as you boil more of that off, the composition changes. So say now it's like 90% water, 10% like ethanol or something. Then it'll become even then the composition will even change further. It'll become 80-20, 40-60, etc. And then since those compositions are now different, a different proportion of water and say ethanol, the boiling point will not be the same because the composition is not the same. But with water will always be water, right? Water 100%. That's why the boiling point is always constant. Okay. So let's move on. So a pure substance. So the thing about pure substance, so when you're looking at these solutions, looking at mixtures in lab, one thing you need to keep in mind is that this is not really I say something to like remember like for exam reading, but it's important to kind of note that a pure substance cannot be distinguished from mixture of uniform appearance. So what we mean by uniform appearance is that the solution or mixture looks exactly one color throughout the whole solution. So it's not like a partition of two different colored solutions. It's like if I have a brown solution, it looks brown throughout, or orange looks orange throughout. And if you compare that to a pure substance, you cannot distinguish it from a mixture and a pure substance based on the macroscopic level. So mixture uniform appearance by observation alone at the macroscopic level. So for example, if I have, say, a common one is, say I have this solution here and it's red. Right? say it's like really red. Now, if I say this is my pure substance. Now, I can't say that if I have something that looks slightly less colored, like, say there's a solution here, but it's slightly like lighter red, right? Lighter like this a little bit. So it looks like the pure substance, but it's actually a mixture. So we say this is the small amount of substance. So the point I'm trying to get at is that we cannot distinguish this one on the right here that's lightly red. We can't distinguish it from a pure substance. So we can't say, based on what we see with our eyes, if what I have here is pure Br2 or a mixture of, sorry, not Br2, but like a mixture of whatever's causing the red color, like whatever substance that is, and whatever, and this one on the right is a mixture. We can't distinguish which one's the mixture or which one's pure, based on the looks, based on what we see on the macroscopic level. So we actually need to use more accurate techniques or instruments to do that. So we can't really say that with our eyes. Okay. So then there's a scheme. So I'm taking this from the slides. There's a scheme in the slide that talks about this, and it's and it want a more like helpful picture of it, I would go through the slides for this particular one. So that's pure substances. Okay. So let's talk about solutions. So you may have heard of solutions, right? You know, when you dissolve something in water, that's a solution. So when we talk about solution, it usually can be any salt, any liquid. So the liquid that dissolves something. So the larger, so say you dissolve like salt in water, right? You add some salt and you add a lot of liquid to dissolve it. The liquid's called the solvent. And they both combine to form a solution. So a solution is a homogeneous mixture of two or more substances. Of molecular. So this is just a very technical definition of molecular or ionic particle size. So when we're talking about chemical compounds, that's the kind of the size scale that we're talking about. So molecular or ionic particle size. So it can be ions, it can be compounds like ethanol, water, stuff like that. So you can actually dissolve water in other solvents. So water can be the solute, but usually when we're talking about inorganic, we're using water as the solvent. So so there's that. So so what do we mean by homogeneous? So you may have heard of this term before. Homogeneous means the same, or what we're talking about is having uniform appearance and uniform properties throughout. So for example, like it looks the same, like the solution as a whole. Like if you look at one part of the solution, it'll look it'll look the same as another part of the solution. For example is, if you have this water bottle right here, and you see it from the bottom, it looks like the same if you look at a point from the top. So that's what we call a uniform or homogeneous solution. When we talk about properties, it means the properties, like physical properties, will be the same. So if you take like, if you were to calculate the concentration of say like one part of the solution versus another part of the solution, it'll be the same. The concentration will be the same. You'll have the same amount of particles per volume or same moles of your substance versus another part of the solution of the same properties. So concentration, another property will be the same appearance. So say for the water bottle, it looks the same as, but we all talked about appearance. What I mean by appearance is color. So the color, if the solution is uniform, the color of the solution will look the same, right? It won't be like one part is more red than the other or more of a color than the other. It'll be the same. So another way to look at homogeneous mixtures is where usually if it's completely dissolved and it's homogeneous, the solution will look transparent and you won't be able to see any tiny particles. So it won't look turbid or cloudy. So that's another property of homogeneous. It's like transparent. So like when you mix two things together, it becomes transparent. Like if you dissolve something in water, for example, dissolving maybe dissolving medicine in water, if it completely dissolves, it'll be a homogeneous mixture. An example, so an example of homogeneous is dissolving sugar in water. Like when you make coffee and you add sugar to the hot water, it'll usually dissolve, right? So that's an example of homogeneous. The example is dissolving sugar in hot water. You'll notice that if you try to dissolve sugar in room temperature water, it won't dissolve right away. So it actually requires some heat. Okay, so that's homogeneous. So the thing about these mixtures now or solutions, we have to talk about phase. So phase usually comes from like when you add two things together, you can have one phase, so you can see part of a solution, or you can see one solution where it's one phase, or there's only like one part, for lack of a better term. It won't be separated by like a layer, for example. If you add solids together, like two different color solids, you'll definitely see like two layers because they're different colors. It's kind of the same thing here when you're adding, like when you're cooking or something. So what we talk about phase is a visibly distinct part of a heterogeneous sample of matter. So what does heterogeneous mean? So it's the opposite of homogeneous. It means different, or having different parts. So what it means is having a non-uniform composition with sorry, let's erase that. With visibly different phases. So different phases, meaning for we'll talk about some examples, but example um, is salad dressing. You know, if you've ever used um, I would say if you ever use like Italian dressing, there's definitely some parts of it that looks liquid, and there's some specks in it that looks that has other parts, like other ingredients in there. So that's an example of a heterogeneous mixture. You have different, visibly different parts that you can distinguish. For example, you may see some parts that are maybe yellow in color, then you see some parts that are black, red, and that's representative of the different ingredients like black pepper, like chopped olives or something like that. So these do apply in real life. So we do see these kinds of mixtures every day. Another example of heterogeneous is like soil. Like you take a sample of soil, you definitely see different parts of a. So mixtures could be solid. It could be any phase, solid versus solid that doesn't dissolve in liquid. That's called like a slurry, or a colloidal mixture. And then there's liquid. You can also have heterogeneous mixtures of liquids where two liquids don't mix. For example, water and ethyl ether, because they have different properties, so they don't dissolve. They won't be miscible or mixed. Cannot be mixed together. So for example is, say you have you took a sample of soil from the ground, or like some salad dressing. So if you take a sample of soil, you're going to pick up some rocks, right? And maybe some leaves or something like that. So that's an example of a heterogeneous mixture. There's probably some other examples for heterogeneous mixtures, but like sand at the beach, you'll definitely pick up rocks in there, right? So sand is another one. And it also contains other. I think it's a combination of different compounds too. So sand is another one. But that's the basics of it, of heterogeneous. Okay. So I talked about homogeneous mixtures. So say if I have pure water and pure ethanol, you can mix them together. They're homogeneous, so they will mix, and you'll form a homogeneous mixture of water and ethanol. So when they're able to mix together, they are called homogeneous. So for example, if I were to show you a beaker of pure water, so here's my water, and here's my beaker of ethanol. So let's make this a little bit of different color. So say ethanol is colorless, but let's just make it black just to keep it consistent, because I don't want you to think that ethanol is blue. Sorry guys. So say I try to mix these two together, right? These mix, so then I'll get a beaker that should be double. So when they're homogeneous, we say that the liquid level should add and increase, right? So let's just draw this to scale again. Sorry guys, I'm not used to lecturing like this. Yeah, I'm just not used to it. Okay, so if we add these two liquids together, we should get mixture, right? So say we get mixture where we double the volume approximately. Okay, that doesn't look double. Sorry. Okay. So say I add those two liquids together and I should pretty much fill my beaker. So if water and ethanol mix, I should get one uniform liquid. So this is a homogeneous mixture. So that's an example of a homogeneous mixture. So they don't mix. Sorry, no, they do mix. Sorry about that. So when they're homogeneous, they'll mix together and form a one uniform looking liquid. So this is an example where they add, and you only see one layer. So you see one phase, one phase. So that's an example of a homogeneous mixture. So now if we add something like water and, you know, maybe something like ether. So ether is a hydrocarbon. So it's very different looking from water. So the thing is, they do not form a uniform mixture. They actually form two layers. So you'll have a layer up here. So this will be my ether. So it looks something like this. You'll see two lines. So you'll see two phases. Sorry, not two lines. And this is water. So you have two phases. So we call this a heterogeneous mixture. We can see we can see two different phases for this compound, or two different parts of the solution. One is clearly on top and one is clearly on the bottom. So these might be hard to spot because the boundary line there, separating the water phase and the ether phase, it can be hard to spot. But it essentially looks like two bodies of water like kind of lined up on each other. So they don't mix to form a uniform solution. You can actually see that boundary line. And yeah, so another example is when you pour water, or sorry, not water, milk into cereal. Like this milk does not dissolve the cereal, right? You always see the cereal float on top. So that's another example of heterogeneous. Okay, I think we covered enough on that. Okay. So I've talked about solids and how they can be mixtures. So next few, if you go to the lecture slides, some examples give you, there's some slides that kind of go into how we work with separating solids from solids, but you don't have to worry about that too much. But the thing I'll talk about, so we're going to talk about next is purification techniques. So there's some examples in the slides that have good representations of that. So I encourage you to go through the slides, you know, at least once, so you know what I'm referring to. But I'm not going to talk about them too much here. Okay. So we're going to talk about separation of mixtures. So let's talk about separation of mixtures. So mixtures are great, but what if we need to like kind of remedy mixtures? For example, you know, wastewater, we need to separate the waste or treat it from the water. So we need techniques to kind of treat and separate sometimes harmful components in wastewater, so we can effectively, you know, recycle it. So one way we can do separate like a mixture of liquids is called distillation. So let's talk about that. So separation of mixtures. Okay, distillation. So what does this what do these methods take advantage of, right? So they so the methods depend on components and their different physical properties. So usually when we separate stuff, we use physical methods. So we're taking advantage of their physical properties and not their chemical properties. In essence, you can use chemical properties to kind of separate stuff, but that's a little bit more tricky. And usually you don't want to do that if you have a compound that you want and you don't want to change it just to separate it from another compound. That's a lot of work, and it's not a very efficient method of doing things. But anyway, distillation. Let's talk about distillation. I'm sure most of you heard of like distilled water. So that's what this basically means. We take advantage of water's boiling point and we evaporate it to isolate pure water. Okay, so it's a process of separating components of a mixture by boiling off and condensing volatile So volatile, what does volatile mean? Volatile means the one that boils off more quickly, or is more likely to enter the gas phase. So usually you need to take advantage of a difference in boiling point, and that's how we're able to kind of purify or separate the two components. So example of this is distilled water. Water, which is water purified by distillation. Okay. So all of these processes rely on physical change. So physical changes. So for example, we're taking our water and evaporating it and taking advantage of its boiling point. So we're inducing a physical change, but we're keeping the identity of the water the same. Okay. So today is the 5th, right? So let's date this the 5th. Okay, let's continue. So we have filtration. So filtration is the process. So, we have, you heard of water filters, right? Or, if you make coffee, use a filter when you ground up maybe coffee beans. So you extract the liquid from the coffee, but you keep all of the other stuff out. So filtration is we take a liquid a mixture of liquid and maybe solid, and we can use a paper filter to collect the solid particles, because the solid particles are usually bigger, and the pores in the paper or the openings will allow liquid to flow through, but not solids. Sometimes though, solids can be really small and they can pass the filter. So in that case, you'll need a more finely specific filter that blocks even the smallest of particles. Okay, so filtration is the process of separating components of a mixture by boiling off. Oh, sorry, no. Sorry, that's what I just said of the other one. Sorry, guys. So it's the process of passing a liquid through a filter. Oops. Through a filter to separate components of a mixture based on relative particle size. So that was what I was talking about. If you have a mixture, maybe you have a solid and a liquid in there. So the solid particles will tend to be aggregated, and so they'll tend to be a little bit more larger than those liquid molecules, which can kind of freely move around within the liquid. So that's a way to separate them, and that's one of the most common ways we separate things in the chem lab when you're usually working with solids as your product. Okay, so this is also based on the physical properties of the components. I'm taking advantage of the size of the particles, and they'll always be the substance in question. So even though I pass it through a filter, you assume that no chemical change occurs. If a chemical change does occur, that is disastrous. So the physical change, even though we pass it through a filter, we're taking advantage of its size, a physical property, and not something of a chemical change or a chemical property. Okay. So these are filtration is very useful for water filtering when you drink tap water. When I was in Davis, the water quality there was pretty bad, so I'd use a water filter to use for my drinking water. It's because the water in Davis tends to be really hard, or it has metal ions in it, which kind of when the water evaporates and dries up, you can see this like this solid white substance, and that's usually caused by magnesium, calcium, or heavy metal ions in the water. So yeah, all my shower, my sinks always be like this weird color because of the hard water, or it has this weird solid stuff around the faucet and stuff, and that's because of the hard water. And we to get rid of that, we use a water filter, to capture those metal compounds in the water. Okay. So There's a picture. So maybe you guys are interested in what a distillation apparatus looks like. So I'll draw that for you. So here's my stand. So here's my stand. And what I have here is so this is called a Bunsen burner. I wouldn't necessarily look at memorize this per se, but if you do go work in the chem lab, you'll see these kind of apparatus in there. So say this is my liquid, right? And this is my gas rising up the flask right there. So here's my liquid, and that's the gas phase. So what we usually have is we have an opening here. So it doesn't look like an opening now, but let me just erase it a little bit. So and usually we have a thermometer here. You have a thermometer here, and it records the temperature. And the long tube that comes along here, that's called a condenser. And what a condenser does is that it allows cooling water to flow through, and that's how you cool down the vapors of the more volatile components. So when you heat up this flask here, the more volatile substance will evaporate and travel through this condenser. So this condenser will be hooked up to water. So usually this is where the cooling water goes out. And this tube right here at the bottom is where we have cooling water in. So this tube right here will fill with water, but you'll notice that there's an interior tube here. So there's actually two tubes. So if we were to look at this in a more zoomed in fashion, there'll actually be a smaller tube in here. So the small tube here is where gas will flow and condense. And this outer tube right here is where the water will go. So when you cool the tube, the temperature of the vapors will reach will go down the boiling point, and the water the liquid will condense in that inner tube and go down to the flask right here. So it'll drip, like water droplets drip, you'll collect your liquid right here. So this is, for example, pure water. For example, you have a mixture of water in the flask and something else. Water can evaporate and you can condense it back to the pure substance. So there's an actually better drawing in the slides, so I would look at that if you're interested, but I will not test this, so don't worry too much. Okay, there's also a drawing for gravity filtration. So if you're interested in gravity filtration, well, I wouldn't say interested, but I'll show you. Gravity filtration is like this. You have a funnel, and in the funnel, you're going to put a little what we call filter paper that blocks this hole right here. So you would pour your liquid or your slurry So say if I have a mixture right here, you'll pour it through here, and it'll empty out into your collection beaker, and where this will be the liquid, and what gets collected at the top right here. So in the filter paper, right here will be your solid. So you have a mixture of solid and liquid. We can separate them by using filtration. So this is gravity filtration. And so yeah, that's an example of filtration that we use for solids and liquids. We won't talk about separation in gases. That's a little more, usually don't separate. Well, I won't say usually, but it's not encountered commonly. So let me just name this. So this is a distillation setup. Okay. So there's some nice nice pictures or schematics of what these two things look like. So don't refer to my drawing. I'm just showing you just a step by step of what they do or what it looks like. So look at the pictures in the lecture slides. But I will the only thing I'll ask you maybe is like I won't ask you to draw these things. Like I'll ask you like maybe name two types of separation methods, and you can pick, gravity filtration and distillation. But having pictures, I know chemistry is always helpful because it's a very abstract discipline. Okay. So we have just telling me I have enough. Okay, about 45 minutes. So now let's talk about types of pure substances. So types of pure substances. So what are substances made of? Well, one is elements. So we have element. An element. So an element is the periodic table. So you have elements that cannot be decomposed into other elements under normal chemical means. So that's what an element is. So a pure substance that cannot be decomposed into other pure substances by normal chemical means. So that means I can't use chemistry to decompose them into other elements or other other basic units of a substance. For example, silver. Silver you cannot corrode. Well, for silver you cannot decompose it further, so it will always exist as silver. So you never find silver in the natural world where it's like something that comes before silver. That's not the case. An example is you have ores, right? But those are compounds, and you can extract silver maybe from an ore. But that's not the same thing as an element. The element is the most basic form of a pure substance. So, and it cannot be decomposed into other like precursor forms of a substance. If that makes sense. Okay. Let's talk about compounds. So as you have pure elements, like pure metals, you have compounds. So these are the ones that can be broken down into pure substances by chemical change. So these are what we say a pure substance that can be broken down into two other into two or more other pure substances by chemical change. For example, if I like say I have a compound that's filled with nitrogen, like there's a bunch of nitrogen atoms in this compound, right? I could react it and use heat and react it with another compound to evolve nitrogen gas. So that's an example where I take this compound filled with nitrogen atoms and maybe some other atoms, and I can decompose it into nitrogen gas. And that has applications in the real world. For example, in airbags, you have compounds called azides, which are filled with compounds with lots of nitrogen in it, and it'll decompose when you hit it with enough force or energy into nitrogen gas. And that reaction is what causes that airbag to deploy when you get into a car accident, because that force will have enough energy to promote the reaction that produces the production of gas, which expands the bag and can save your life. Okay. So compounds, they're pure substances that can be broken down into other pure substances. Elements, they are the purest form of a substance and cannot be decomposed to other pure substances by ordinary chemical means. There is ways to convert elements into other elements, but that's a whole nother topic, and we're not going to talk about that. It's nuclear chemistry, and those are not normal chemical reactions because you're reacting it with high energy particles, and the chemistry is usually between two compounds, so two chemicals, two relatively maybe stable compounds that can produce a reaction, like stable on its own, but when they interact with each other, they're reactive. That's not the same for nuclear chemistry. That's dealing with high energy particles that affect the nucleus of atoms and therefore affects the identity of the element you're talking about. So we need to talk about what compounds are different from mixtures. Okay, sorry guys. So let's go over this little Venn diagram. Well, not Venn diagram, but mixtures. So we have, so mixtures are impure, right? They're composed of more than one substance. So we separate them. So separation by physical methods. Physical, let's just say means. So we use physical properties to take advantage of them. And then they're separated into compounds and elements. So we can use this for elements and for compounds. For example, if I have solid iron, so that's an element. That's not a compound. So a compound is made of two or more atoms of different elements. For example, water. So we can do that for both elements and compounds. The example for elements is where you have two solids. So we can separate, for example, sulfur and iron. They're both solids, so we can separate them by taking advantage of their physical properties. One of them being magnetism, where iron will be attracted to a magnet, but sulfur will not. So that was that sulfur iron example that I didn't go over here, but that's an example of separating elements. So we can also, so this was the other thing I was talking about, separation of compounds by chemical means. What you do is you separate the elements in a compound by taking advantage of its chemistry. So that's useful when you're trying to make a different compound, but that's not useful if you're trying to isolate, say, that's not something you do for a mixture. So you wouldn't react the mixture by chemical means to separate them, because typically in a mixture you want one of the components and you don't want the other. But in compounds, you want a different compound, so we react it. So we're separating, the atoms of the compound by decomposing it to other pure substances that are different. So this is an example of using chemical properties to separate the components of a compound. So compounds, say we have compounds are pure, right? So compounds, they're pure because a compound is such as water, so it's pure and like pure water, right? Or like another compound, maybe methane or ethanol or something. Compounds will always be pure. A mixture of two compounds, sorry, a combination of two compounds is a mixture. So don't get those two confused. But compounds by itself, when you have only one compound, it's pure. So we can separation by chemical means. And we get elements pure and or compounds pure. Okay. So let's list some examples. So here's some examples of common elements. So some examples of common elements is like, so in pencils we have granite. which is a form of carbon. Pennies. So we have, well, everyone knows about pennies, but that's copper. So, and some other ones we have, like jewelry, nickel, or some other kinds of metals. And usually, we have wires, like metal wiring. So pennies is also copper, but we also have like wires. That's an example of copper. And then there's some other ones. So then we have also other materials that are made of like iron, like nickel. I also talk about jewelry. So jewelry are composed of metals like silverware, silver, stuff like that. Compounds. Some common compounds are like, like medicine, drugs. Then there's examples of compounds like branded medicines, drugs. So like, for example, Tylenol or Advil. And so those are specific compounds in them, and they're not like single elements or single elements in the periodic table. So they're a mixture of them. Another one is baking soda. Which is sodium bicarbonate, and sodium bicarbonate looks like this. So we see here that it's composed of sodium atom, hydrogen atom, carbon atom, and 3 oxygen atoms. So those are examples of compounds. So another compound, water's a compound. Most of your food contains amino acids, proteins, and those are compounds too. They're composed of many, many atoms. And like toothpaste is composed of like sodium fluoride. So a source of fluoride, that's a compound. And all the other things. And then there's stuff like chalk. Let me just look up what chalk is made of. I don't remember. Yeah, so the main component of chalk that we used to teach, it's mostly calcium carbonate. So carbonates are very important. They're found naturally, especially in ores and stuff. So like rocks. So these are examples of compounds that we see in our everyday life. Okay. Okay, so we talked about representations of these substances. So usually we use the element symbol, so representations. So let's talk about representations of pure substances. So we have elemental symbols, for example, there's a one or two-letter abbreviation for the element in question. So for example, H is hydrogen, He is helium. Then you have some very weird ones that do not make sense. For example, W is for tungsten. And I believe it's because usually there's some kind of history behind it. Yeah, so it's usually because of another reason. For example, tungsten. It's actually used with a W because it comes from the mineral called the wolframite. So it's usually called tungsten or wolfram. So that's why W gets its name. So there's usually a historical reason or where it's extracted from. But tungsten is not one of the elements you have to memorize or know for the quizzes or for the exams. So don't worry too much about random ones like that. The ones that some of them also don't. Some of them also don't make sense, like sodium. So Na is sodium. So, but it's a one-letter or two-letter abbreviation of the element symbol. So it's used to represent in writing the name of the element. So in communications, you always see these symbols. So you'll it's good to be aware of what they mean. Okay. So we have the element symbols, then we have chemical formulas. So chemical formulas, they're a symbolic representation of a pure substance. We combine it with subject numbers to denote the number of atoms in the formula or formula unit. For example, sodium chloride. So we know we have one sodium atom and one chlorine atom. So that's table salt as an example. So let me just put this right here. Yeah. Oops, sorry. And so we also have so we also have other examples too, where it's not one. So so example, we have H2. So this denotes how many number of atoms in the elements. There's also some different, I won't say different, but some formulas can get complicated, so they're usually abbreviated by atom number. So in this case, hydrogen has 2 hydrogen atoms. And then like the example we show above, we have like calcium carbonate. So this part carbonate here is actually a separate species. So it's actually separated into something called ions. So we have calcium 2 plus. So that's an ion for calcium. Don't worry about the charges right now. I'm just telling you what they're made up of. And then we have CO3 2 minus. So this whole unit here is 2 minus. But what the subscripts means that this is called the carbonate ion. So what the carbonate ion means is it's composed of 1 carbon atom and 3 oxygen atoms bonded together. Don't worry about what the bonding means at this point. We're just talking about the subscripts and the chemical, what they mean in chemical formulas. Okay. All right. So we can have instances of like multi-elements. So for example, hydrogen. So if I have a multi-element compound, or it won't be a in this case we call it a molecule. So when we have like say for example a hydrogen, like a species like this, the H2, that's called a hydrogen molecule. So we use that number to denote that there's 2 hydrogens that make up this molecule. So we'll learn more about molecules like this, but there's that instance, and there's also the instance of where we have multi-element molecules for like calcium carbonate, something like sodium chloride, HCl, water. So these numbers denote how many atoms make up that molecule or that compound. Okay, and those you might be asking, what's the difference between a molecule and a compound? Well, the compound represents like a large like when you're talking about like a single unit or a single like a single molecule, we say they're molecules. Like it's like the individual units of a compound. For example, the sodium chloride compound, we say there's a bulk of sodium chloride. When we're talking about sodium chloride as a whole, we say the sodium chloride compound, the compound sodium chloride. But when we're talking about like the individual units or molecules, we talk about the molecules, so the individual units. And in terms of like ionic compounds like sodium chloride, we refer to them as units and not molecules. But we'll get more into that later. Okay, guys, that is it for today. We'll wrap up chapter 2. We'll wrap up chapter 2 next on Thursday. I know it's kind of slow right now, but I think this is the best way to kind of do things since I'm not there in person. If I was in person, I would definitely it's known to go a little bit fast. So I just want to take it slow because there's lots of information to digest. So if you have any feedback, let me know. But this is it for today's lecture. If you have any questions, just always feel free to email me, and I'll see you Thursday. All right, guys. Bye.